Okay, so in this video, we will consider a very nice application of the Monotone Convergence Theorem. So here's the problem. We want to show that the recursive sequence converges using the Monotone Convergence Theorem. And this is the first time that we consider a recursive sequence. The term recursive means that to obtain the next term of your sequence, you have to know the previous term. And you can see here, we're calling the sequence S, so S1 is defined to be 1, and to obtain the next term of your sequence, Sn plus 1, you need to take the previous term Sn and add to your previous term 1 over n plus 1 squared. And you might wonder why, first, am I using an S instead of an A? And second, why am I using an uppercase N instead of a lowercase n? Because since this point, we've always used a lowercase n. Now we're using S and an uppercase N. Well, if we start trying to find the first few terms of this sequence, you'll see very quickly why we use an S instead of an A, and why we use an uppercase N instead of a lowercase n. And we will then prove that this sequence will converge using, of course, the Monotone Convergence Theorem. So let's first find the first few terms of our sequence. So S2, so we already have S1. S1 is defined to be 1. How do we find S2, the second term of our sequence? Well, to get S2 here, you must take n to be 1. So then you'll have that S2 will be S1 plus 1 over 1 plus 1 is 2, so 1 over 2 squared. But we know S1. S1 is taken to be 1. So this is 1 plus 1 over 2 squared. Let's find S3, the third term of our sequence. Well, to get S3, we take n to be now equal to 2. So if n is 2, we have that S2 plus 1, 3, equals S2 plus 1 over 2 plus 1, 3 squared. And you see S3 depends on S2, but we have just found S2. So let's replace. S2 is 1 plus 1 over 2 squared, plus, of course, the leftover term, 1 over 3 squared. Let's find S4, and hopefully by then we'll see a pattern. S4, well, to obtain S4, n must be taken to be 3, so S4 will be S3 plus 1 over 3 plus 1, 4 squared. So you see S4 depends on S3, but we have just found S3. So let's replace S3 by this expression. Plus, of course, the leftover term, 1 over 4 squared. And now at least you should begin to understand why we're using an S instead of an A. Because you see that the terms of our sequence are actually sums. S1 is the sum of one number. S2 is the sum of two numbers. S3 is the sum of three numbers. S4 is the sum of four numbers, and so forth. And let's now see if we can find the general pattern for Sn. If you see, S1 is 1. S2 is 1 plus 1 over 2 squared. So we go up to 2. S3 is 1 plus 1 over 2 squared plus 1 over 3 squared. So we go up to 3. S4 is 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared. So we go up to 4. And in each case, S1 we're summing one term. S2 we're summing two terms. S3 we're summing three terms. S4 we're summing 4 terms, so in general, Sn we are summing n terms. Well, they all begin at 1. Plus, then we have 1 over 2 squared. plus then we have 1 over 3 squared. And where do we stop? Well, S2 we stop at 2, S3 we stop at 3, S4 we stop at 4, Sn we stop at n. So 1 over uppercase n squared. So Sn for any n is the sum up to n of the reciprocals of the square. 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared up to 1 over uppercase n squared. And we can write this concisely using sigma notation. And now you will understand why we use an uppercase n instead of a lowercase n. So we are summing. They are exactly n terms, uppercase n terms. So we'll end at uppercase n, will begin at 1, and we need a dummy variable to capture the change in the denominator. The power of 2 always stays there, but then we have 1, 2, 3, 4 up to uppercase n, and here we'll use as our dummy variable a lowercase n. And you can check. So we are summing 1 over lowercase n squared, as lowercase n goes from 1 to uppercase n. So when n is 1, 1 over 1 squared is 1, check. Plus, when n goes up to 2, 1 over 2 squared, check. Plus, when n goes up to 3, 1 over 3 squared, check. And n goes all the way up to uppercase n, plus 1 over uppercase n squared, check. And that's why we used an uppercase n to begin with, so that we could use a lowercase n as our dummy variable. Okay, so now we have our sequence explicitly, no longer from the recursive definition, but quite simply, the nth term of our sequence is the sum from 1 to n of 1 over lowercase n squared. And now we want to prove that this sequence converges. So that's the claim. And here's something interesting will come up. Well, a sequence converges if the limit of the sequence is a real number. So the limit of the nth term of our sequence, as n goes to infinity, exists. So that this is a real number. We'll call this, say, L for limit. The limit of our sequence as n goes to infinity exists, and it's some real number. That's the claim. So the sequence does converge. But let's just look at what this limit may look like if we look at the formula for Sn being the sum of 1 over n squared from 1 to uppercase n. And then we'll see something interesting popping up. I'm just now replacing Sn by its concise expression using sigma notation. And this should remind you a little bit of an improper integral. We are summing from 1 to uppercase n, 1 over lowercase n squared, and we are letting uppercase n tend to infinity. So we could write this even more concisely as the sum of 1 over n squared, n going from 1 to, and now we're going up to n, but we're letting n go to infinity, so we can simply write the upper bound as infinity and drop the limit. So what we're saying is that this object is just a real number. But what's neat is that this is now an infinite sum, right? As n, we're adding up n positive integers, and as we're letting n tend to infinity, we're adding more and more and more numbers. In the limit, we're adding an infinite number of real numbers. And we can now write this out explicitly. And this is our first example of a so-called infinite series. So we have when n is 1, 1 over 1 squared is 1, plus when n is 2, 1 over 2 squared, plus when n is 3, 1 over 3 squared, plus when n is 4, 1 over 4 squared, plus when n is 5, 1 over 5 squared, and so forth. And in the limit, because as n we're adding n terms, and as we let n tend to infinity, the number of terms that we're adding tends to infinity. Therefore, in the limit, we have an infinite sum of real numbers. And what we're now saying is that this infinite sum does exist, and it's some real number. So let's prove that we're actually correct. And as we have said, we will prove that we are correct using the monotone convergence theorem. So we have to show that two conditions are met. First, that the sequence is either increasing or decreasing. Second, that it is bounded. So let's prove first that the sequence is increasing. This will be a very simple proof. So if we just go back to our recursive definition, Sn plus 1 was defined to be Sn plus the positive number 1 over n plus 1 squared. So if you do Sn plus 1 minus Sn, you get 1 over n plus 1 squared. As n is a positive integer, this will be strictly positive, so it's strictly larger than 0. So Sn plus 1 minus Sn is strictly larger than 0. Add Sn on both sides, therefore Sn plus 1 is strictly larger than Sn. So if you move one step further in the sequence, the next term is strictly bigger than the previous term. Therefore, the sequence is increasing. So we're halfway done. We now have a monotonic sequence as it is increasing. It remains to prove that the sequence is also bounded. And now to prove it is bounded, we will not use the recursive definition, but we will use our closed form of the sequence using our sigma notation. So let me just look at the sum again. If you recall, Sn is the sum of the reciprocals of the square from 1 to uppercase n, which you can write very concisely using sigma notation as the sum as lowercase n goes from 1 to uppercase n of 1 over lowercase n squared. And now we have to prove that this is bounded for every n. Well, we're adding up positive numbers, so the sum is always at least 0 for every n. Right? S1 was 1, S2 is 1 plus 1 over 2 squared, S3 is 1 plus 1 over 2 squared plus 1 over 3 squared, and so forth. So every term of our sequence is positive. So we have a lower bound. What about now an upper bound? Well, it's not clear how big this can get, but the key point is, if we look at this, we can think of it as a Riemann sum. So we can look now at the function 1 over x squared and try to compare this Riemann sum to the area below 1 over x squared. So let's see if we can accomplish this. And this is an argument we've used in the past. If you look back to when we tried to figure out how big was n factorial. Again, our function is 1 over x squared. It's a positive and decreasing function. And we're interested in the function from the interval from 1 to n. for n, of course, is n minus 1. So, let me construct rectangles where the area of each rectangle is a given term of our sum. So I will take from the interval from 0 to 1 the height at the right-hand point to give me the height of my rectangle. And I will do so for every other rectangle. So for each interval, I take the y value at the right-hand point to give me the height of my rectangle up to the last interval. Now let's see. So the area of each rectangle is the length of the base times the height, but the width of each rectangle is 1. So the area is simply the height of the rectangle. The height here is, well, 1 over 1 squared is 1. So the area of this rectangle is 1. The height here is 1 over 2 squared. So the area of this rectangle is 1 over 2 squared. The height here is 1 over 3 squared. So the area is 1 over 3 squared. Up to here, the height is 1 over uppercase n squared. So the area is 1 over uppercase n squared. And now, there is one thing we have to be careful. So we could be naive here and say, well, the sum of these n positive integers is the total sum of the areas of all of these rectangles. The area here is 1, plus the area of this, which is 1 over 2 squared, plus the area of this, which is 1 over 3 squared, up to plus the area of the last rectangle, which is 1 over n squared. So geometrically, Sn is the sum of the area of all of these rectangles. This is clearly less than the area below 1 over x squared from 0 to n. But here we have a little bit of a problem. From 0 to n, the function shoots up to infinity, so we're taking something that is way too large. What we'll do is we'll start integrating at 1. So we'll take this 1 out. So we'll keep the 1 as 1. So we will ignore the 1 over x squared part from 0 to 1. And we'll just keep the real number 1 as 1. And then we will compare the remaining of the sum with the area below 1 over x squared. And so you see, this sum is now the total area of these rectangles. And we can see this will be less than the exact area below 1 over x squared, starting at 1 and ending at n. But this is exactly the definite integral of 1 over x squared from 1 to n. The problem is we now have an upper bound, but it still depends on n. We need a fixed upper bound that does not depend on n. Well, this can be easily achieved. What if we don't stop at n? What if we integrate 1 over x squared all the way up to positive infinity? This will be clearly true. If you think about it, when you integrate 1 over x squared from 1 to n, you get the area below 1 over x squared from 1 to n. But as n is finite, no matter how big n is, it's always less than infinity. So here we're adding even more area, and this is true for any given n. We now have an upper bound. Hopefully, this will be finite. This is a very simple improper integral. The antiderivative of 1 over x squared is negative 1 over x. And if you evaluate this improper integral, you should find that the area is simply, let me double check, equal to 1. So in the end, for every n, Sn is no bigger than 1 plus 1, which is 2. And now we have proved that Sn is bounded. For any n, Sn lies between 0 and 2. And again, I leave this up to you. This will take you one line. So the sequence Sn is bounded. As for every value of n, the sequence lies between 0 and 2. But wait, we have previously proved that the sequence was increasing, and now the sequence is proved to be bounded, so we have an increasing and bounded sequence. Therefore, by the monotone convergence theorem, the sequence converges. And again, we will write this as MCT. And we have our conclusion. The sequence converges by the monotone convergence theorem. Let's now go back to what this means in terms of the limit, right? Since the sequence converges, as n goes to infinity, the sequence will be approaching a fixed real number. And what will this look like? We've already written this down. This is what we had. This was our claim, that the sequence converged to some real number. Now we have proved this by proving it was bounded and increasing. The monotone convergence theorem kicks in, which proves that we are right. The sequence will converge as n approaches infinity to some real number. Why am I going back to this statement? Because it's just so nice. The sequence converging, the sequence being the sum of the reciprocals of the square from 1 to uppercase n, and as n goes to infinity, the limit of the sequence gives us our first example of an infinite sum, an infinite series. We are adding here in the limit an infinite number of positive real numbers. And the wild thing is, this actually exists. This is a real number. What we do know with our lower and upper bounds is that this infinite sum, if you keep adding plus 1 over 6 squared, plus 1 over 7 squared, and you never stop, you will get some real number. We have proved that it lies somewhere between 0 and 2. Now the question is of knowing the exact value of this infinite sum of the limit of our sequence is much more difficult. To figure out the exact value of this infinite sum is a very challenging problem. But just so you're aware of it, and I think you'll appreciate this, it can be proved that this infinite series, the limit of our converging sequence, not only is between 0 and 2, which we have just proved, but actually happens to be exactly, and here, fasten your seatbelt, pi squared over 6. And this is rather unexpected. And you can try, and I encourage you to do so, take out your calculator and start adding up these numbers. 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over 25 plus 1 over 36 plus 1 over 49 plus 1 over 64, and keep adding those. And the more you will be adding, the closer you will get to pi squared over 6. So calculate this with your calculator, add these numbers up to a given point, and compare how close they are to each other. And the more numbers you keep adding of this type, the reciprocals of the square, the closer you will get to pi squared over 6. Just a wild equality. And as I've said, proving this is a whole different story.